Picture this. A brand new suspension bridge stretches across a narrow channel of water in Washington state. It's elegant, thin, modern, almost too perfect. And then it starts to move. Not a little. Not the gentle sway you expect on a big bridge. It rises and falls in slow, rolling waves, like a ribbon being shaken from one end. People laugh at first. They give it a nickname, Galloping Gertie. But on a windy day in 1940, the motion changes. The bridge doesn't just bounce, it begins to twist. One side up, the other side down. Back and forth, over and over, until the steel itself can't take the rhythm anymore. And in a matter of minutes, an entire span tears apart and drops into the water below. Here's the mystery. This wasn't a hurricane, it wasn't an earthquake, and it wasn't some freak gust that struck once and vanished. So, what actually happened? How can just wind bring down a bridge that was designed, engineered, and built by professionals? And more importantly, what did this collapse teach engineers about how structures can fail, not from one big force, but from a feedback loop? By the end of this video, you'll understand the real mechanism behind the Tacoma Narrows Bridge collapse, why the usual resonance explanation is incomplete, and how modern bridges are designed to avoid this exact trap. Because the lesson of Tacoma Narrows isn't that engineers were careless. It's that the bridge didn't fail like a static object. It failed like a system that learned, a system that started to steal energy from the air. And once that theft begins, it's terrifyingly hard to stop. Let's start with what people think they know. Most of us have heard the word resonance. The idea that if you push something at just the right rhythm, the motion grows. Like pumping your legs on a swing, like tapping a glass until it sings. So it's tempting to say the wind matched the bridge's natural frequency, and that's why it collapsed. But wind doesn't push like a hand on a swing. Wind is messy. Wind gusts. Wind shifts. Wind swirls. And what happened at Tacoma Narrows wasn't the bridge being pushed in time, like a child on a playground. What happened was closer to something else. A microphone. You've seen it before. Someone walks too close to a speaker with a live mic, and suddenly you get that high-pitched scream, a sound that feeds itself. The mic hears the speaker amplifies the mic, and the loop tightens until it becomes unbearable. That's not resonance in the simple push-at-the-right-time way. That's feedback, a self-excited instability. And Tacoma Narrows, in a very real sense, turned the wind into a loudspeaker and the bridge into a microphone. The bridge didn't need the wind to be perfectly timed. It only needed the wind to keep feeding the loop. Now, why was this bridge so vulnerable to that loop? To understand that, we need to step back and look at the design trend of the era. Suspension bridges are magical because they let you span huge distances with relatively little material. The cables carry the weight, towers hold the cables, and the deck hangs below. But the deck still matters, because the deck is where people and vehicles actually travel, and a bridge deck has two jobs. 1. It has to be strong enough to carry loads. 2. It has to be stiff and stable enough to resist motion. Early long-span suspension bridges tended to have deeper, more open truss structures along the sides. That made the deck bulky, but it also did something important. It let wind pass through. It didn't turn the bridge into a smooth, aerodynamic shape. It kept it leaky. And leaky shapes are often easier to live with in wind because they don't build up as much pressure difference from one side to the other. But Tacoma Narrows was different. It was slender, streamlined. It had solid side girders instead of a big open truss. It looked modern, and it saved weight and cost. And in a purely static sense, it worked. If you parked vehicles on it, it could hold them. If you measured stress under normal loads, it could handle it. But the bridge wasn't failing under a static load. It was failing under a moving, coupled system, air plus structure. And that modern deck shape changed the rules of the game. Right away, Tacoma Narrows started telling on itself. Soon after opening, it was clear the bridge could move in wind in a way that made people uneasy. The motion wasn't always twisting at first. Often it was vertical, a long, rolling up and down wave that traveled along the roadway. If you were a driver, it might feel like you were going over slow ocean swells, except you were suspended in air. And here's a key question to hold on to. Why did the bridge start with that vertical gallop and then later shift into a torsional twist? Those are different kinds of motion. Different modes, different dangers. The bridge was basically saying, I can move this way, and I can also move that way. And one of those ways is survivable. The other is fatal. We'll come back to that. Now, let's talk about the wind. Wind doesn't just hit a structure. Wind flows around it. And when air flows around an object, especially one with sharp edges, it tends to separate, reattach, and shed vortices, swirling pockets of rotating air. If you've ever seen a flag flap, you've seen vortices at work. The flag bends, the airflow changes, a vortex peels off, the flag snaps back, and the cycle repeats. The important thing is this. The motion of the object changes the flow, and the flow changes the forces on the object. That's a loop. So the real question becomes, does that loop remove energy from the motion, like friction? Or does it add energy to the motion, like a push? If it removes energy, the motion damps out. If it adds energy, the motion grows. And Tacoma Narrows, under the right conditions, cross the line into adds energy. This is where the twisting matters. When a bridge deck twists, one side rises while the other falls. That changes the angle the wind sees. Instead of air hitting a flat surface, the deck becomes a rotating wing. And wings, by design, create lift. Now, I'm not saying the bridge became an airplane, but the same principle applies. Angle plus airflow can create an upward force, and if that upward force happens at the wrong time, it doesn't oppose the motion, it amplifies it. Imagine you're twisting a board back and forth. If someone pushes down on the side that's already going down, they're helping you twist faster. That's what the wind can do to a torsional motion. And if the timing locks in, the wind keeps paying into the motion like an investor that never runs out of cash. That phenomenon has a name: flutter. Aeroelastic flutter. It's not just forced vibration. It's self-excitation. The structure moves, the airflow reacts, the reaction reinforces the movement, and the cycle intensifies. Once flutter starts, the motion can grow even if the wind speed stays steady. Because the wind isn't a one-time shove. It's a continuous energy source. Now let's go back to that earlier question. Why did the bridge start with vertical motion and then shift to twisting? One reason is that different modes have different thresholds. A bridge can be easy to excite vertically in mild conditions, especially if it has low damping. That can create the famous galloping look. But torsional flutter often requires the system to cross a specific stability boundary. It's like tipping a canoe. You can wobble safely for a while, but once you pass a certain angle, the recovery doesn't happen. On the day of the collapse, the bridge didn't just bounce. It found the unstable mode, and once it found it, it stayed there. It was locked into a motion that the airflow kept rewarding. So what did that look like in real time? A steady wind funnels through a narrow passage. Drivers approach the bridge and see it moving, but it's still standing. Some people turn around, some keep going. The deck begins to twist more clearly now. One side up, the other down, and then the opposite. You can imagine standing on it and watching the railing on your left rise while the railing on your right drops, like the bridge is trying to wring itself out. And here's another question to hold. Why didn't the motion average out? Why didn't the bridge just flex and settle into a new equilibrium? Because in flutter, equilibrium is not stable. The system doesn't seek a calm center. It seeks the edge. And once the structure is feeding with the airflow, every cycle can become slightly bigger than the last. Until the materials are no longer behaving like springs. They're behaving like something else. They're yielding. Connections are loosening. Steel is bending where it was never meant to bend repeatedly. And fatigue and fracture don't care that the bridge was strong enough on paper. They care about cycles. They care about repeated stress reversals. They care about motion that keeps coming back. Eventually, pieces begin to fail. A hanger connection here. A joint there. The deck starts to tear. A section of roadway breaks loose. And once the deck continuity is compromised, the suspension system is no longer distributing loads the way it was designed to. The bridge's geometry, the very thing holding it in shape, is collapsing. Then a full section drops. Not in a clean singular snap, but in a cascading failure where each break makes the next break more likely. The span disintegrates into separate moving parts, and the water below receives what gravity always collects, the final outcome. So, what did engineers learn from Tacoma Narrows? They learned that wind load isn't just a pressure you calculate and apply. It's a conversation, a dynamic interaction between structure and fluid. They learned that stiffness alone is not enough. Damping matters, aerodynamics matter, torsional stability matters. They learned that a sleek, solid-sided deck can behave very differently from an open truss. And they learned that you can build something that is perfectly adequate under static assumptions and still have it fail spectacularly under dynamic reality. In the years that followed, bridge engineering changed. Wind tunnel testing became more common for long spans. Deck shapes were refined to be more aerodynamically stable, often designed to reduce the tendency for the wind to grab and amplify torsion. Engineers developed better models for aeroelastic behavior and learned to watch for the warning signs of flutter and other instabilities. And, crucially, Tacoma Narrows became a teaching tool, not as a punchline, as a reminder that nature doesn't care about your spreadsheet if your assumptions are wrong. Now, let's close the loop with the deeper lesson. The collapse wasn't wind versus bridge, it was wind plus bridge, a coupled system. And that system can either dissipate energy or generate motion. Tacoma Narrows crossed into a regime where the system generated motion. It began to self-excite. And once a structure is self-exciting, you don't need a dramatic external event to keep it going. You just need the environment to keep supplying the energy the structure is asking for. That's why the collapse feels so eerie. Because it doesn't look like a sudden attack. It looks like the bridge is doing it to itself. So here's the takeaway. The most dangerous failures are not always the ones where something is too weak. Sometimes, the danger is that something is too willing to move. And if the environment can reward that movement, the structure may drift from stable to unstable without ever crossing a load limit in the way we normally imagine. Tacoma Narrows taught engineers to treat wind as a dynamic partner, not a static force. It taught them to respect feedback loops. And it taught them that in the real world, failure is often not a moment. It's a mechanism that builds, cycle by cycle, until the last cycle is the one you remember. In the next episode, if you want, we can take on a different kind of engineering story, a mega project where the failure isn't a dramatic collapse, but a slow disaster of schedules, costs, and risk compounding over years. And if you're curious, I'll also publish the diagrams and the failure chain map for Tacoma Narrows alongside the sources, so you can see exactly how the mechanism unfolds step by step. Because the point of these stories isn't spectacle, it's understanding.